Everybody's more or less here. Okay, so today we're going to talk about spectral concentration of Boolean functions and a little bit about learning theory. So I'm kind of happy because I feel we kind of got through the basics, and now we can start talking about topics and applications and things. So in particular, one application we'll talk about for this class and the next class is in theory of machine learning. So this is motivated by real-world machine learning, although it's a very theoretical model for it. And we're going to see, roughly speaking, how sometimes you can show that simple functions have simple Fourier spectra and therefore can be learned efficiently by simple algorithms. So let me introduce the model of learning theory that we'll talk about. It's a variation of the PAC model due to Valiant. And it's specifically concerned with learning functions whose domain is the Boolean cube, which we think of with the uniform distribution. So the model is kind of similar to the model we talked about when we were talking about property testing, in that you should imagine that you have some kind of access to a function, a Boolean valued function on the cube, but you don't know exactly what it is. It's unknown to you. There's two kinds of access types that you might have to it. So it could be that you have what's called query access. And that's the access model we talked about when we were talking about property testing. And that it just means that you can take any string you want. If you're the algorithm and you're trying to learn this unknown function, you can take any string you want, give it to the black box, and it'll give you back f of x. Okay, so you can pick as many strings as you want and learn the value of f on each of these strings. That's one kind of access. A weaker access model where the algorithm does not have as much power is called random examples. And in this model, it can't just pick any string it wants. Basically, it just says, give me an example. Like, it pushes a button, and it gets a uniformly distributed string and the value on that string. So it can push this button as many times as it wants and get f values on uniformly random and independently chosen points. Okay, so the algorithm has more power in this case and less power in this case. Okay, and as you might expect from the name, the goal of an algorithm that interacts with this unknown function is to try and learn what it is. So its goal will be to output a hypothesis function that ideally is the same as the unknown function. But that's a pretty stringent requirement. So we're also going to potentially allow it to make a hypothesis which is not quite correct. So we want to, let's say, ensure that the distance of the hypothesis from the function, the normalized distance, is at most some epsilon, which is a parameter you can think of the algorithm, the learning algorithm, as knowing. So remember this. The definition of this is the probability over a random x that h of x differs from f of x. And we're going to allow the algorithm to be a randomized algorithm for trying to learn f. Especially in this case, there's already randomness going into the whole picture because the examples that the algorithm gets are random. So we're also only going to insist that this happens with high probability. And I'm not going to dwell too much on what this means. You can just imagine it meaning, say, probability at least 9/10. The 9/10 is arbitrary. You can make it higher with the expense of a little bit more running time. OK, so that's the model. And if this were it, if f could be any old function at all, then this is not a very interesting problem in that it's like very hard. I mean, if f is an arbitrary function, let's assume you even have query access to f. If you need to output like a hypothesis that's correct or that agrees with f on almost all the inputs, then there's nothing you can really do. You just have to like query almost all the inputs. Okay? Or if you have random examples, you have to just like wait around until you've seen almost all the different inputs. Okay? And both of these strategies are going to take something almost like 2 to the n time. Okay, so I guess you can learn any function in something like 2 to the n time, but that is not considered very efficient in computational complexity. But there's nothing you can do. So what we usually do to get around this is make the assumption that we're not trying to learn a completely arbitrary function. Like, perhaps we're assuming that this function whose behavior we're trying to learn about is not arbitrary. And the way to formalize this is actually much like in property testing. You assume that f belongs to some class of functions C that you know about. OK, so this C is called the concept class. And it's a collection of Boolean functions. OK, and now the learning problem, which is an algorithms problem, is potentially more interesting. I mean, if C is a simple enough class or an interesting class, you may be able to learn it in one of these two access models in, let's say, polynomial time. That's the usual basic goal in the theory of algorithms and complexity. Any questions so far? So yeah, in some sense, the goal of this class will be to show that for some interesting classes, they'll have every function in that class will have some simple enough Fourier expansion, which will in turn mean that a relatively efficient algorithm can learn any function in that class. But let's do an example that will tie back in to what we were talking about with property testing and testing linearity, just to make sure that we have the model down. So let's imagine the learning problem in the case where we're trying to learn an unknown parity, or linear over f2 function. So let's imagine the concept class, which is all functions that are parities of some subsets of the bits. OK, so what are we going to do? You have black box access to a function, and somebody promises you this is a parity function. And now you want to output a hypothesis function which is close to it. Or for simplicity, let's say in this case you really want to get error 0. You actually want to determine exactly what the function is. Yeah?
Could do it one bit, like this kind of thing where one bit is -1 if 1, and then just see if it outputs -1.
Yeah, that's right. So I think Marla is suggesting a way to, let's say you have queries, a way you can learn the function exactly with n queries. And actually, let me, for the purposes of this, switch back to f2 notation. And we'll even let the output be f2. OK, so we have black box access to some function, and we know that f is some parity. So in the back of our minds, we know that f of x in this notation is sum of ai xi, I goes from 1 to n, where the ai's are like unknown coefficients. Okay, and our problem is equivalent if we're trying to learn with error 0 to figuring out what these ai's are. OK, so Marla's suggestion was if we have queries, what we can do is just query on, let's say, E1 through En. Or remember, EI is the string 0, and that has a 1 in the ith place. And in this case, when you do this query, this will exactly give you back, this will give you A1, and in general, querying on EI will give you AI. OK, so with n queries, you can exactly determine what the unknown parity is. And the running time for this, I guess, would be something like O of n squared, because even just, I don't know, writing down an n-bit query takes you n time. So I don't want to get too much into running time details. Let's just say we're happy that this is polynomial in n. OK, so what if you don't have queries? Can somebody make a suggestion? Now you just have random examples.
I just have a question.
Yeah.
In this summation that you have for f of x,
Yeah.
should that just be I and some s there?
You could either sum the xi's for I in a set S, or you could sum overall I through 1 through n, and ai's are 0 or 1 coefficients. Yeah. Yeah, Misha?
And random queries, then it's just n linear equations. We can think over independent.
Yeah, exactly right. So one thing you could do is, if you have random examples, every time you get like a random example, you'll get some string x, and you get f of x, where x is random. And that's really like an equation in the AIs. You know, if we take this formula, every time we get an example, this is some numbers, 0 or 1, which we know, and these are numbers, 0 or 1, which we know. So we get like an equation in, this gives us an equation in the unknowns AI. And if we, let's say, did n random examples, we would have n equations in n unknowns. And we might hope that they were linearly independent. And if they were linearly independent, then we could solve them and recover the AIs. So if we got n linearly independent equations, then we're done. And they might not be, but it's quite easy to see that, I don't know, if you take many more than n equations, let's say if you take c times n examples, where c is a big constant, then with high probability, you'll get n linearly independent equations somewhere within there. OK, so I won't do that calculation. It's easy, but this is how you do it. Draw, let's say, 100 times n examples with high probability. That'll give you 100 equations, and the 100 times n equations in the n unknowns, a1 through an. With high probability, the sum n of them will be full rank, and you can find those n efficiently, and you can solve the system equations efficiently, all using Gaussian elimination. Yeah?
When we do random examples, do we have to decide how many times we're going to sample before we start sampling?
Turns out not to really matter, but for simplicity, assume you don't. So assume you can draw a bunch of examples and then do some calculations. And if you want more examples, go ahead. And if you're satisfied, stop. Any other questions about this? OK, so that's the model. And this was all about, in the case of learning linear functions or parities, it's not too hard to learn them even with error 0. But we'll see later that it's kind of important in most cases that you allow yourself a little error. OK, so what's another example of an interesting class of relatively simple functions that we might try to learn? Well, I'll mention one that will occupy us a little bit for the next two classes. It's a popular class in machine learning theory. And it's the class of, say, polynomial size decision trees. So possibly you've seen the definition of a decision tree before. If not, it's too annoying to actually make it, so I'll define it by example. So a decision tree is some kind of object, which I'll draw. It's the representation of a Boolean function. And it looks something like this. So you imagine that first it queries some coordinate of the n input coordinates, say x1. And then there are two possible outcomes. x1 could either be -1 or it could be +1. So maybe in this case, if it's x1, it's -1, the decision tree might decide to query x2. And then this could be -1 or it could be +1. And maybe in this case, if they're both -1, then the tree is done. And it says, I know the value of f. The value is 1. In this case, maybe it says, I'm still not sure the value of f, so I'm going to query x3. And that's -1. Then maybe the value of f is -1. And if it's +1, maybe the value of f is +1. And it doesn't have to do things in the same order. So maybe if it queries x1 and it sees that that's +1, now it decides to query x3, -1, +1. Maybe in this case the function's 1. In this case it decides to query x2. Maybe the function's -1 here, and maybe it's +1 here. OK, so I said in words what was happening, but if it wasn't clear, a decision tree is a picture that looks like this. It's a binary tree. Each of the internal nodes is labeled by a variable. And each of the leaves is labeled by a number. And it computes a Boolean function in sort of the obvious way. All the outgoing edges are labeled +or -1. We can even let it compute a function into the reals. These numbers in the boxes could be any real numbers. And it computes a Boolean function as follows. Given an input, x1 through xn, you sort of follow the path down the tree that it's describing, and you sort of output the box that you end up in. Any questions about that? Does it kind of make sense? I believe if I drew this right, I believe this is the function f of x1, x2, x3, which is 1 if and only if the bits are in sorted order, either increasing or decreasing. But maybe I got it wrong. So if you verify or anti-verify that, let me know.
You can't conclude that's true by just examining x1 and x3, right?
Sometimes you can. If x1 is -1 and x3 is +1, then this will be true regardless of x2's value.
Oh, yeah.
So yeah, it's interesting. Sometimes, though the function depends on all three coordinates, sometimes if you query them in an interesting order, you can become convinced of the value of f, even though you haven't read all of the input coordinates. And that's somehow the idea of decision trees. It could be that even though you have a Boolean function whose truth table has 2 to the n entries, it may be sort of compactly representable by a decision tree like this. OK, and this kind of potentially compact representation for Boolean functions comes up in, learning theory, for example. People often try to model unknown functions by, simple decision trees that explain their behavior by a sort of sequence of yes/no answers for the values of the bits. OK, question? All right, so one thing we'll show next time is that functions that have compact representations like this can be learned efficiently in the query access model. In the stronger model where you have queries, you can learn functions computed by compact decision trees effectively. So actually, let me mention 2 more definitions here related to decision trees. The size of a decision tree, usually written S, is the number of leaves. And the depth, more often I'll write K instead of D, is the length of the longest, well, it's like the depth, length of the longest route to leaf path. OK, so the depth of this guy is 3, and the size is 6. And as I said, one thing we'll show next time is the theorem due to Cauchy, Levitz, and Mansour from 1993 is let C be the concept class of all Boolean functions that are computable by a size S decision tree. And it's learnable with queries in the query access model to error epsilon in time which is polynomial in all the relevant parameters. And s and 1 over epsilon. OK, so we're going to prove this next time eventually. And it'll all be because functions computed by small-sized decision trees have relatively simple Fourier expansions. OK. So as I said, there's a connection between learning theory and the simplicity of a Fourier expansion. And we'll talk about one sort of meta-algorithm for learning unknown Boolean functions, which works pretty well if the functions have a simple Fourier expansion. So let's define a little bit more carefully what I mean by this phrase, have a simple Fourier expansion. So let's make this definition. Let f be a collection of monomials or Fourier coefficients, so of subsets S. And we'll say that a function f is concentrated on f. More precisely, epsilon concentrated on f, just if all but f of epsilon of its Fourier weight is sitting inside these coefficients. Which is to say, if the sum over all coefficients which are not in the collection f of the Fourier weight, meaning f hat s squared, is at most epsilon. Okay, so again, mostly think about the case where f is a Boolean valued function, so the sum of all the Fourier coefficients squared is 1. Epsilon is a small number. To say that f is spectrally epsilon concentrated on this set f is to say that if you look at the sum of all the weights, sums up to 1, 1 minus epsilon of them are sitting inside this collection f. And one particular special case, which is important, if f is the collection of all sets f, s of cardinality at most k, we say that f is epsilon concentrated up to degree k. Okay, and that's like saying it's like saying the sum over I greater than k of the weight at level I of f is at most epsilon. Okay? And this is probably the most common collection of monomials that we'll be interested in concentration on. As I mentioned maybe in the first class, one typical phenomenon is that functions that are combinatorially simple often have most of their Fourier spectrum on low degree monomials, which corresponds to index sets of small cardinality. OK, so we'll talk about just that fact later. What kinds of functions have this nice property that their Fourier spectrum is concentrated maybe on the low degree monomials, or at least on some relatively small collection of monomials. But let's spend some time thinking about why that's good if it occurs for learning theory. So I'm going to describe sort of a meta-learning algorithm, which works great whenever this happens for some relatively small collection script f. So here, let me call this a learning theorem. OK, so let's say you're given the weaker kind of access model, just random examples from f. And suppose somehow you know that this condition holds for a set script f that you know. Now, that's not necessarily going to happen always, but for the sake of this thing, this theorem, suppose you know that when I say you, I guess I mean a learning algorithm, know that some collection script f such that f is, let's say, epsilon over 2 concentrated on script f. Then you can learn f efficiently in terms of the size of script f. You can learn f to error epsilon in time polynomial in all the parameters, n, cardinality of script f, and 1 over epsilon. So what this is saying is if you happen to know or have reason to believe that f has got most of its spectrum concentrated on this set script f, then you're kind of done. And the idea is quite simple. What you're going to do is estimate all of f's Fourier coefficients on coefficients in the set f. And that's quite easy to get very good estimates for them. And then, roughly speaking, once you have that, you have, by definition, almost all of f's Fourier spectrum. So it's kind of like you basically know the function f. And we'll see that that's enough to actually allow you to output a hypothesis that is indeed epsilon close to f. So to put that into actual proof is not too difficult. It's based on a couple of propositions. So one just says that for any particular Fourier coefficient you're interested in, you can estimate it very accurately, quite efficiently. So for a fixed subset S, you can compute some number, which I'll write f twiddle of S, such that it's very close to the truth. F twiddle S minus the true Fourier coefficient f hat S is at most epsilon. OK, there's some chance of error, so we'll say except with probability at most delta in time polynomial in n 1 over epsilon. And the dependence on delta is even better. It's log 1 over delta. OK, so given epsilon and delta and a particular Fourier coefficient you want to compute, with high probability, you can compute it very nearly, quite efficiently. Can somebody tell me how to do that? OK, let me give you a hint. Suppose S happened to be the empty set. OK, so you're interested in estimating f hat the empty set. What is that equal to? It's the mean of the function. OK, so now you have random example access from f. You can just draw strings x at random and learn f of x. So how would you estimate the mean of the function? Yeah, just draw a bunch of random samples and estimate the mean. And that will work just like this by Chernoff bound. OK, and what if S is not the empty set? Exactly, multiply the output by chi of S. All right, so the proof is like this. You're trying to compute f hat S, which by definition is the expectation over a uniformly random f x of f of x times x, well, the S monomial, the product of xi for I in S. Now take a look at this. This is a random variable, if you think of x as random. This is a number in -1, 1, actually. In fact, it's enough that this is a number strictly between -1 and 1, or in the interval. And you can also compute it, I mean, efficiently in, I don't know, linear time, given a particular x, f of x. That's like what you get when you ask for a random example. So this is just some random variable that you can, have independent draws from. And it's bounded between -1 and 1. So you're just trying to estimate the mean of an unknown random variable. And you get this kind of fact by Chernoff bound. So I'm not going to spell it all out, but I'm sure you've seen it before. This implies that with something like 1 over epsilon squared times log 1 over delta samples, the empirical average will satisfy this condition that we want. This condition. Should I say any more about that? A question? OK, great. So that's just one Fourier coefficient. OK, so if we're still trying to prove this theorem, naturally what the algorithm is going to do is just basically apply this proposition to each of the Fourier coefficients in script f. And maybe it's going to set this epsilon to be much smaller than this one. And it's going to set delta to be pretty small, so it makes sure that all of its estimates are likely to be correct. And having done that, it'll more or less have the Fourier coefficients of the unknown function. So what should it actually do once it knows all these Fourier coefficients? It's still got to output a hypothesis that's close to f. Its hypothesis is supposed to be a function whose range is plus or minus 1. So do you have a suggestion?
We could compute what our hypothesis. Well, we know the Fourier range coefficient, so we could calculate what output it gives and round it up to 1 minus 1.
Yeah, the only last step is to round it off to plus or minus 1, whichever is closer, or take the sign of what it computes. So the other proposition we'll need is this one. Let f be a Boolean function, a Boolean valued function, and let g be a function whose range potentially is the real numbers. And then let h be defined by h of x is the sign of g of x. OK, so h's range now is plus or minus 1. OK, and if g happens to be 0, it doesn't matter. You can let it be either plus or minus. And the proposition says that if f and g are close in 2-norm, then h is close to f. OK, so it's just saying that if as a real number g's value is quite close to f, which is always plus or minus 1, then if you rounded that off to plus or minus 1, forming h, you're typically going to get the right value, f of x. So the proof of this is, whenever x is a string such that f of x, how shall I write this? F of x minus g of x is at least 1, then whenever x is such that f of x does not equal the sign of g of x, then f of x minus g of x should be at least 1. Right? Because f is either plus or minus 1. Let's say it's plus 1. If g is negative, then it's at least 1 away from f. And similarly, if f is minus 1. Okay? In fact, I'll just also write square here. It's the same statement. So therefore, the distance of h from f, by definition, is the probability over x that f of x does not equal h of x. So let's say it's the expectation over x of the indicator for this. And remember, h is just the sign of g of x. So let me write this as the indicator that f of x does not equal the sign of g of x. Okay, and as we just observed, whenever that indicator is 1, the difference between f and g squared is at least 1. So if I call this star, star is at least, is at most the expected value of f of x minus g of x squared. Because point-wise, whenever this is 1, this thing is at least 1. And this is, by definition, f minus g 2 norm squared. Any question about that calculation? OK, so now we're ready to prove this theorem and put it together. And the algorithm is just what I said. Estimate all the Fourier coefficients really closely, and then output the sign of sort of your approximation of the Fourier expansion. OK, so what we'll do is for each, or what the algorithm will do is for each s in f, estimate f hat s to within, let me see, root epsilon over 2, square root the cardinality of script f, so quite small number, with the confidence parameter delta equals 1 over 10 times the cardinality of f. And how much time does this take? Well, it takes, each one of these takes time inverse polynomial in this, logarithmic in that. So overall, it will be polynomial in n, cardinality of f, 1 over epsilon, and log of this. So that's it. We might get another factor of script f, because we have to do this for all the coefficients, but that's all hidden inside the polynomial. And we know by doing a union bound over all sets S in script f, even except with probability at most 1 over 10, all of the estimates are, let's just say, accurate. Meaning your estimate of this number, f hat s, which we call f twiddle s, is correct within plus or minus that. OK, and now we'll output, the last step of the algorithm will be output h of x equals sine of the sum over all s in script f of the estimate f twiddle s times x s. And we should call this function g of x. OK, so this is a real valued function, g of x, that the algorithm can compute, and then it outputs their sign. Of course, our goal is to show that the distance of h from f, which is the final error of the learning algorithm's hypothesis, is at most epsilon. So we can use this proposition, and it remains to show that the distance in 2 norm squared between f and g is at most epsilon. OK, so this quantity, the 2 norm squared between f and g, is by definition the sum over s of f minus g hat s squared, which is the sum of f hat s minus g hat s squared over all s. And we'll just split this sum up into the guys that are in f and the guys that aren't. So this is at most the sum over s in f of f hat s minus g hat s squared plus the sum over s that are not in f f hat s minus g hat s squared. Okay, and let's just do a few calculations here. What is this number here? Yeah, it's 0 because, I mean, this is the definition of G, and it only has non-zero Fourier coefficients. This is the Fourier expansion of G on the guys that are not in F. So this is 0. So this term is just this, but that's at most epsilon over 2 by hypothesis. Remember, our hypothesis is that F is epsilon over 2 concentrated on this set of coefficients script F. And as for this, well, each quantity here, oh, sorry, what is this number in terms of something earlier? It's up here. Ankit? Thank you. Yeah, it's F tilde S. OK, so this is just the difference between the estimate F tilde and the real value F hat. Which we know is at most this. So this is at most sum over s in script f, the square of that. So it's epsilon over 4 times the cardinality of f plus epsilon over 2. And so that's at most epsilon over 4 plus epsilon over 2. So we're done even with a quarter epsilon to spare. OK, any questions? Yeah.
Does it make a difference if you use the same queries to calculate all of the different F tilde hats?
Oh, that's a terrific question. The question was, does it make a difference if you use all the same queries to calculate or estimate F twiddle S for each S, or should you use fresh queries? With this analysis, it actually doesn't make any difference. You can just draw one batch of examples, which is the number of examples you need to estimate 1, and use that batch to actually estimate all the Fourier coefficients for S in script F. Because really, we ultimately only use the union bound here, which means that even if the estimations are not independent, it's OK. We're just going to add up all the failure properties. So yeah, it's actually quite interesting to think about if you would actually look back what this thing is. It's some empirical estimate of fxxs. And if you use all the same query points to estimate, or not query points, the random examples to estimate the F twiddles, then if you plug that in and expand it out, you actually see what you get is something kind of interesting. It's like the sum over a bunch of empirical samples of F's value on that sample times something to do with the Hamming distance between X and the sample point. But it's not, you think, maybe you should just take some decreasing function of the Hamming distance. So that, the sample points that are closest to the one you're trying to hypothesize on get their F values weighted higher than the further ones. But actually, it's not quite like that. So I was going to put this on the homework, but I didn't. But you should write down what the actual hypothesis is more carefully if you used all the same samples to estimate the Fourier coefficients. OK, so this is, for today at least, the last thing I want to say about algorithms for the most part. Well, I'll say one more thing. So this learning algorithm says that if you're trying to learn some unknown function f, and for whatever reason you become convinced that f has most of its Fourier weights concentrated on some set script f, and you know script f, then you're kind of done. You can estimate those coefficients and go ahead. That, of course, evades the question of, how are you going to find this set script f? And next time we'll see the algorithm called the Goldreich-Levin algorithm, which interestingly was originally developed for cryptography, not for learning theory. But Kushlevitz and Mansour pointed out the connection to learning theory. And this algorithm has the cool property that if you're given queries access to f, you can actually find all of its large Fourier coefficients, which is a bit amazing because there are 2 to the n possibilities. But nevertheless, with some nice tricks that we'll see, you can actually figure out where they are. So you can figure out where this best set script f is, and then go to town. Without that algorithm, or if you don't have query access, so you can't run that algorithm, for the most part, the best thing that you can do is just like hope that if you take script f to be all the low degree monomials, that would work. Okay, and that suggests what's called the low degree algorithm due to Kushilevitz and Mansour. And it just says that suppose you know, I mean, it's an immediate corollary. Suppose you know that f is epsilon, well, let me say that, yeah, it's epsilon concentrated up to degree k. For all f in this concept class, then epsilon over 2, then f is, c is learnable to error epsilon in time, polynomial in, well, n, 1 over epsilon, and what else? Well, it's basically you're just going to run this learning theorem where f is the set of all monomials of degree at most k. So there's something like at most n to the k of them. In fact, there's actually at most n to the k of them. So this is the size of script f. Okay, so if you know that all the functions in your class have most of their Fourier coefficients concentrated at low degree, like k, then you can learn that class in time, something like n to the k. And what's cool about that is it reduces an algorithmic problem. You know, how can I learn this unknown function f, or this unknown class of functions c, to an analytic problem. Just prove that all the functions in script c have their Fourier spectrum concentrated at low levels. Okay, so once you know this theorem, you can forget algorithms and like the learning algorithms and learning model, and just know that as soon as I have an analytic result, like every function from my favorite class is concentrated up to degree k, then I get like a learning result about that class for free. All right, so that motivates trying to prove such results of the form, you know, every function with such and such property has most of its spectrum at low levels. So I'll show you a few results like that. Here's the first one. It's very simple. Let f be a Boolean function. Then for all epsilon, f is epsilon concentrated up to degree total influence of f over epsilon. Okay, so if you happen to know that f's total influence is small, and this is some combinatorial quantity, the sum of its influences, then you also know that its Fourier spectrum is concentrated at relatively low degree. And the proof of this is very simple. It's kind of like identical to the proof of Markov's inequality. So the total influence of f has a Fourier formula. Does somebody want to tell me what it is? Somebody who remembers? Yeah, it's sum over all s of cardinality of s, f hat s squared. So if you think of these as weights, it's kind of like the weighted average of the cardinalities of the sets. Okay, and in particular, if f, suppose this were false, it were not concentrated. So if the sum over sets s of degree at least total influence of f over epsilon s squared were bigger than epsilon, well, by way of contradiction, then in this sum, for all of these terms, this thing is at least epsilon. So you'll be getting at least epsilon times, well, at least this. The sum over s of cardinality of s, f hat s squared, would be at least would be, in fact, greater than total influence of f over epsilon times epsilon, which is a contradiction. Okay, so therefore this has to be at most epsilon. Okay, it's like the same proof as like Markov's inequality. Okay, so that's great. So do we immediately get any interesting learning results? Well, I'll tell you one that's kind of interesting. If you recall, when we were talking about voting, one thing that we proved was that for all f, the sum of the degree 1 Fourier coefficients was maximized by the majority function. And, don't harass me about what happens if n is not odd here. That was a very easy proof. That's what Rousseau asked us to prove. And we also know that this quantity, the sum of f hat I, is equal to the total influence of f if f is monotone. Right? Because if f is monotone, we saw that f hat I is the same as the ith influence. So the sum is the total influence. Now, majority is a monotone function, so it's also true of that. So this is equal to the total influence of majority. And remember, in majority, each coordinate had influence something like 1 over root n, so the total influence is order of root n. Okay, this is something we did a couple lectures ago. We saw that every monotone function's total influence is at most constant root n. Okay, so we can just immediately deduce that every monotone function is basically concentrated on degree up to root n. So therefore, if C is the class of all monotone functions, this is epsilon concentrated on degree at most root n over epsilon. Okay, and therefore it's learnable from random examples to error epsilon in time. Well, something that's not awesome. Polynomial in n to the root n and 1 over epsilon. But it's not too horrible. So remember, the time to learn any function is something like 2 to the n. And this is more like exponential in root n. So in some sense, it's a substantial savings. It's also kind of pretty great because the class of all monotone functions is pretty wide. That's a fairly rich class. You're doing something in sub-exponential time. So it's not bad. In fact, it's also known that you can't really improve on 2 to the root n. So both this upper bound and that lower bound are due to Bashuti and Taimon. And it's even a bit, sub-exponential time is even interesting because, as we'll see next time, there's some connection between, learning and cryptography. I mean, in cryptography, they're kind of the opposites of one another. In cryptography, you have some maybe unknown function or one-way function. You're hoping that it can't be learned efficiently from examples. And in cryptography, they're really, paranoid. So they want to make sure all their problems are really, really hard to solve, like 2 to the n time. And this shows that you can do something interesting in time much less than 2 to the n for monotone functions. Yeah?
But if we require the hypothesis to be monotone, is there anything?
Whew, that's a good question. You're saying if you run the low-degree algorithm, what you get might not be a monotone function. I don't know what's known. I don't know. Good question. You might, well, I have some theories on what you might try, but I'll save them for later. Okay. Great. So that was one learning result that came quite for free based on simple Fourier stuff we've done. Let's look again at majority. We saw that it's had total influence root n, so we know that most of its Fourier spectrum is on below degree root n. Actually, something much stronger is true for majority. It's much better concentrated than this upper bound. And to see this, we'll use this notion of noise sensitivity that we talked about last time. That was the probability, the noise sensitivity at delta of majority. It's the probability if you take a random string, look at the majority, then flip each bit with probability delta. What's the probability that that flips the overall outcome? If you remember, I told you this is something like root delta. So this is actually true for all n and delta. In fact, I'll even put in a number here. You can put like, I don't know, 2. And this actually tells us something much stronger about the concentration of majority's Fourier spectrum. Remember, this is a half minus a half, the noise stability at 1 minus 2 delta of majority. I hope you remember these things. I just do this trick because this is the thing that has a nice Fourier formula. Let me factor out the half. 1 minus this noise stability is the sum over all s of this factor, 1 minus 2 delta, to the cardinality of s times f hat s squared. Okay, so these are all based on formulas from last time. And now look what's going on here. We're saying we know that this whole quantity is at most root delta times 2. And let me put the half over there in my mind as well. So it's saying this thing in the parentheses is really small. Now, for very large values of s, this thing is going to be really small. It's going to be like negligible. So the contribution from really large s's here is going to be small. You're subtracting it from 1. So you're not going to get like a very small answer by subtracting a small number from 1. So what I'm trying to say is this actually kind of proves that almost all of the contribution has to be coming from the small sets s. Basically, once s is bigger than 1 over delta, the contribution here is negligible. So if you're going to get a small number by subtracting from 1, remembering that these things add up to 1, most of it must be coming from sets of size at most 1 over delta. Okay, so actually that sort of shows you, and I'll do this calculation a little bit more carefully, that for a fixed constant epsilon, you have almost all but epsilon of majority's Fourier spectrum on constant degree, independent of n. All right, so let me say something more general, because really we only used here the fact that majority's noise sensitivity was small. So let me do the following pretty simple proof. It's only slightly harder than the proof of this proposition. So this will only be for Boolean functions, Boolean valued functions. Let's say it has its noise sensitivity. Okay, just any function f is epsilon concentrated on degree up to 1 over delta, where epsilon is, let's say, 3 times the noise sensitivity at delta. Okay, this is for all delta between 0 and a half, let's say. Okay, so for any delta, you get concentration up to degree 1 over delta as long as the noise sensitivity at delta is small. Okay, so let's just use this formula. Remember this thing, sorry, this should have said majority in the special case of majority, but in general we have this formula. Okay, so let me put this factor of 2 on this side and say that by definition, 2 times the noise sensitivity at delta of f is sort of by definition 1 minus sum over s, 1 minus 2 delta to the cardinality of s, f hat s squared. And remember, this thing 1 is actually equal to the sum of f hat s squared over all s. That's Parseval. So I can put those two sums together and actually say that this is sum over s 1 minus 1 minus 2 delta to the cardinality of s times f hat s squared. You see, because if I broke this back up, the second piece would be this exponential factor times f hat s squared, and the other piece would be sum over s of 1 times f hat s squared, which is 1. This is just a little algebraic trick. Now this is a non-negative number, and it's actually increasing as a function of cardinality s. So what I'm saying is I can sum over all s at least 1 over delta. Well, first of all, I could just put in this number times f hat s squared. I would just be dropping some terms if I did that. But since this is an increasing parameter in cardinality of s, like the lowest this could be is if I actually plug in cardinality of s equals 1 over delta. So what I'm saying is all of these guys, when s is at least 1 over delta, are at least 1 minus 2 delta to the 1 over delta f hat s squared. Is that OK? And now I have something like 1 minus 2 delta to the 1 over delta. That's something like e to the minus 2. In fact, it's true that this is at least sum over s greater than or equal to 1 over delta, 1 minus e to the minus 2 f hat s squared. OK, and 1 minus e to the minus 2 is some number, and it's at least 2/3, as it happens. So if I bring the 2/3 to the other side, I get 3 ns delta f is at least some s bigger than 1 over delta of f hat s squared. Okay, and that's exactly the desired conclusion. The Fourier weight above degree 1 over delta is at most 3 times noise sensitivity. OK, if you got slightly lost in that calculation, which I would if I didn't have the piece of paper in front of me, don't worry about it. I mean, the idea is kind of clear once you see this formula. OK, and so in particular, since we know this fact, I can say that, let's say, the majority on n function is epsilon concentrated up to degree big O of what? Is it too easy? Well, this is like root delta. So to write delta in terms of epsilon, we would have delta as roughly epsilon squared. So I get concentration to degree something like O of 1 over epsilon squared. OK, so ignoring this O, to get all but 1% of majority's Fourier spectrum, Fourier weights, you have to go up to degree O of 10,000. But for each epsilon, it's a constant. OK, now that's just about one function, which is not so awesome necessarily. But actually, there's a theorem that we'll see in a couple of weeks called Perez's theorem, which actually says that for all weighted majority functions, f, you have the same bound. The noise sensitivity at delta of f is at most, let's say, 2 times root delta. And it's kind of easy to guess. I mean, if you're interested in all weighted majority functions, the sort of two extremes for weighted majority functions are majority, for which we know it's bounded by root delta. That's where like all the coefficients are equal. And the case where all the coefficients are like maximally unequal is like a dictator function. And for a dictator, the noise sensitivity at delta of a dictator is delta, which is even smaller than 2 root delta. So you might guess that this is true. Indeed, it is true. So it implies that for all weighted majorities, we have epsilon concentration on degree up to O of 1 over epsilon squared. And so by the low degree algorithm, you can learn, let's see, C, the class of all weighted majorities. It's learnable from random examples only to error epsilon in time. Remember, it's something like n to this, so polynomial in n to the 1 over epsilon squared, which is polynomial time if epsilon is a constant. Any questions about that? Actually, that's not so great, because another algorithm will learn this class, the class of all weighted majorities, just in time polynomial in n and 1 over epsilon. So it's not exponential in epsilon. So this looks kind of bad. But as you'll see on your homework, this is like a much more flexible approach to learning weighted majorities. This algorithm uses linear programming, and it doesn't extend very well. So you actually see that you can learn much more expressive classes that are related to the class of weighted majorities using the low degree algorithm. And the same analysis easily gives you this sort of polynomial running time. And weighted majorities, also known as linear threshold functions or half spaces, are like the favorite concept class in all of machine learning. So that's relevant to this particular class is quite relevant for learning theory. OK, so last thing I want to do is come back to another very popular class in learning theory, which is the class of decision trees, which we talked about earlier. And similarly, try to show that they have very simple Fourier spectrum that are quite concentrated, and therefore they're relatively efficiently learnable. So let's draw another picture of a decision tree. I won't draw such an elaborate picture as before. Maybe we have some leaves here, or maybe you query some other variable here, okay, etc. Now, let's fix a particular path in this decision tree. P be a path, by which I mean a root to leaf path. So since the only good root to leaf path I have on the board is this one, let me fix that. Let's say that's P. OK, and remember, this is -1, +1, -1. And let 1p be the indicator function. Let me use range 0, 1 of all the inputs x which follow the path p. OK, so in this particular picture, this is the function which is the 0, 1 indicator of all strings that have, let me make this 4 for fun, x1 equal to -1, x2 equal to +1, and x4 equal to -1. OK, so far I haven't said anything about the leaf value. OK, so by simple interpolation, you've seen this before. In this case, this example case, this is just the and of some literals. It's in particular like 1/2 minus x1 over 2 times 1/2 plus x2 over 2 times 1/2 minus x4 over 2. Right? This says you better have x1 equal to -1, x2 equal to +1, x4 equal to -1, else you're 0. And as we'll see in a second, you can actually write down the Fourier expansion for a function computed by a decision tree in a very simple way based on the Fourier expansion of each of the paths. You can probably, or possibly, even see that now. But before we quite get there, let me make a few observations about the spectral simplicity of these kinds of functions, ands of literals. So let's say the tree has depth at most k. So let's see. Each path function in the tree, path indicator, 1p, has Fourier degree at most k. Okay, because every path, you write down the Fourier expansion, it'll look like this. Each path is length at most k, so the highest degree you'll get is k. That's good. It also has, at most, 2 to the k non-zero Fourier coefficients. Okay, because again, you have at most k terms here, each of which has 2. You expand it all out, you'll get at most 2 to the k non-zero coefficients. So that's also pretty simple. Sometimes I'll use the notation, the sparsity of the Fourier transform is at most 2 to the k. So that's a way in which it's simple. Another way in which it's simple is actually the sum of all the Fourier coefficients in absolute value is at most, what can I write here? In fact, I can write equality here. Yeah, I can even write equality here. What's that?
Just the sum for S for the size of S less than k?
Just over all of them. I mean, in particular, you'll the only non-zero ones will be ones that have degree at most k. Yeah, 1. Because if you just expand this all out and then sum all the absolute values of the Fourier coefficients, actually every Fourier coefficient will be plus or minus 1 over 2 to the k if there are k terms. I guess I should write, well, if it has exactly k terms, every Fourier coefficient will be like 1 over 2 to the k, plus or minus. And there will be 2 to the k of them. So you add them all up, you'll get 1. OK. And actually, just to say again, something I've already said, each Fourier coefficient will actually be of the form integer over 2 to the k. If there's exactly k of terms, then every one will be plus or minus 1 over 2 to the k. If there's then fewer than k, then it'll be some even integer over 2 to the k. OK, any questions about that? This is all a setup to show that we're going to show that since each of these paths has a very simple Fourier expansion, it satisfies all these properties, overall, the Fourier expansion of the function computed by the decision tree is also very simple. So if, let's say, f is computed by this tree, we also say that has size at most s, then how can I write the Fourier expansion of f, or the multilinear representation of f, in terms of these path indicators? All right, I'll get you started. It's the sum over all paths p of the indicator of that path It gives you 1 or 0 for the event that you follow the path times, yeah, the value of the leaf at that path, which maybe I might denote by f of p. This is the value of the leaf at the path. And this is correct because each input x makes exactly one path true. Right? Every input goes down some path. So if you look at the collection of all functions 1 sub p, each input makes one of them 1 and the rest of them 0. So you can write f's expansion by like taking the indicator for the path and multiplying it by the appropriate value. Does that make sense? You look slightly stunned. I think it makes sense. OK, and the last thing we're going to do is use that fact to show that actually f's Fourier expansion is quite simple. So therefore, what can we say about the Fourier degree of f? Yeah, it's at most k, because each of these terms, just a constant times 1p, is a polynomial of degree at most k. So it's the sum of guys with degree at most k. This degree is at most k. It has at most, or its Fourier sparsity, well, you're summing up s many. There are s paths. S paths, each of these path indicators has sparsity at most 2 to the k. So we get at that most that. Also, s is at most 2 to the k itself. So that's at most 4 to the k. Okay, if you have depth k, you have at most 2 to the k leaves. This thing, which as you'll see in the homework, is sometimes called the Fourier one norm. It's the sum over s of f hat s in absolute value. Well, again, each of these things has Fourier one norm at most 1. It's not hard to see that if you add up a bunch of, that this really is a norm. And so therefore, this is at most s times 1. OK, or at most 2 to the k. And each Fourier coefficient, f hat s, is also going to be of the form integer over 2 to the k. OK, so all of which is to say that if you're a function computed by, let's say, a depth k decision tree, then you have a very simple Fourier spectrum in some sense. Your degree is at most k. You have at most 4 to the k non-zero terms. They're all kind of granular, like they're either 0 or they're not too small. OK, so that's all quite nice stuff. So let me just say spend 1 second to say the learning conclusion. Well, certainly we also have that the total influence of f is at most k, because all of the non-zero Fourier coefficients are at degree at most k. And therefore, we know from the low-degree algorithm, you can learn depth k decision trees to error epsilon in time, polynomial in n to the k and epsilon. I'll make one last observation in words. Why will you have any error in this algorithm? What are the sources of error? If you look back at the low-degree algorithm, there's 2 sources of error. One is you sort of only stop looking for the Fourier coefficients up to some degree k. And you just say, well, I'm assuming that there's a most epsilon weight above level k. Actually, here there's 0 weight above level k. So you're actually not losing anything there. What's the other source of error? It's that you're estimating the Fourier coefficients empirically. You might not get them exactly correct. But actually, you know that each one is of the form integer over 2 to the k. So any estimate you get, if you set epsilon to be like less than 1 over 2 to the k, then you can just take your estimate, round it off to the nearest multiple of 1 over 2 to the k, and it'll be exactly correct. So once you learn to error 1 over 2 to the k, because you know this granularity of the Fourier coefficients, you can just round off all your estimates and get it exactly. So in fact, you can learn to error 0 in time polynomial n to the k. So that's pretty cool. You can actually identify the unknown decision tree in time poly n to the depth.
But there is still a probability.
Yeah, with high probability. Yeah. Okay. See you next time.